All right. So we're live for episode 2 of Nand2Tetris. And I think we have a little bit of refining to do. So in the last session, what we did was kind of go over the specifications, and I'll put up some screenshots here. Oh, where's my whiteboard? Okay. Oh, I hate this notice. Okay. So last time around, we went through some specifications and just kind of digested it, started to understand how how the machine code is encoded in binary, and what the assembly looks like. So that's mostly this up here in the top left. So we have an assembly instruction looks roughly like this. There is some destination or like multiple destinations possibly, a computation, and then a jump instruction based on the result of that computation. And that's every assembly instruction. This jump part is optional. Um, and even this destination here is optional. And when those translate down to machine code, these 7 bits here represent the operation. And we have these 3 bits are the destination, and then the jump effect. So we started kind of pseudocode modeling that at a couple layers. So we worked on the machine code layer, the assembly layer, and also kind of the state machine for the hack machine itself. So that's its memory and its registers and program counter and whatnot. Um, yeah, and the way I like to do things here, especially in a stream like this where I have time, is I like to distill a model. Basically like fully specify it, share everything I know with the compiler. That way the compiler can kind of let me know if my understanding is correct. I don't feel like a problem is fully solved until it's like properly distilled. Like the final code, I want it to read kind of like an instruction manual in itself, right? It doesn't just make it work. It fully kind of specifies constraints, maybe even things I hadn't realized were constraints until I started implementing it. So that's what we'll do. Let's jump back into all the pseudocode from last week, and I'm gonna try and see if I understand what I was doing. All right, so there's the emulator planning. Let's take a look at the sheet first, actually. Um, okay, so this is kind of like our to-do wish list. Yeah, so we want to be able to run the compiled, yeah, so I'll call this the wish list. Um, and then I guess this is explanation of the architecture. We'll do this here. Okay. Um, excuse me. Okay, we could start by taking a look back at the architecture, maybe applying anything that we learned from last time, just to see where we are, and then we'll go from there up layers into the machine code and then into the assembly. I think the assembly will be the most complicated. So, state. All right. So the machine has ROM, which is memory, and RAM, and then 3 little registers. Um, yeah, and I'm just calling these things binary. It's going to be an int. But they have actually different use cases here. So this D register is always data. A is an address. Address or data can be treated either way, cast depending on the instruction being run. Um, so that's potentially interesting if we're to like model that strictly. And a program counter is always going to be an address. So A gets used to update the program counter or to access memory, either here or here. Or sometimes it gets used to collect compute a value, which then might be saved to D or like elsewhere. D might be something that's pulled out of well, usually it's gonna be something that's pulled out of RAM, or maybe assigned from A. Um, right. So there's this M here, this virtual. It kind of works sort of like a register, but this will always be like referring to RAM A. Right, so when you're implementing this as a circuit, it's kind of always wired up. So that M is just pointed there depending on what the value of A is. And sometimes it's meaningless because you're going to use A as a constant, and sometimes it's actually going to be the next thing. Similarly, current instruction uses a program counter into the ROM. And what's this? Execute ML instruction. Ah, right. So wait, I did leave everything in an uncompiling state. So that's going to be our first step. We're going to make sure everything compiles. And then go into refining everything a little bit. So we're going to execute some sort of instruction. And I guess we've decided to use ml.instruction. We'll call that inst. Is that a type that exists? So ml package, here we go. Yeah, we have an ml.instruction here. So ML being our machine language. So we have a machine language instruction, and it gives us a new state of some sort. Symbolic register values, I think that's actually this M. No, that's like the R. Right, all of these. Stack pointer, I guess, is SP, local arg this, that. Which, that won't really mean anything until much later. But there are all of these. These are what are called the, they're kind of like, so they're virtual registers, I believe, is what they're called. So R0 through R15. And their purpose will be made clear in later chapters. We're just kind of like taking that for word right now, which I don't love. I kind of want to understand. So I'll probably go back to thinking about this as we proceed. Great. So there's that. Let's take a look at the machine language. Okay, so everything is binary for now. So if you see my Cinecore project, I use like opaque type aliases. So basically, there's an underlying int, but it's typed in different ways for like unsigned 15, and for the various types that are being used. That's because like everything here is just binary, and it's easy to use something in the wrong place if it's all just the same type. So at some point, I'll probably give that some more refinement. I'm not sure where that's going yet. There's an A instruction, so it takes binary, which could mean an address or a constant. But it only really means that at the level, I suppose, of all the A instruction ever really means is that load the A register with that value. Right, so it doesn't really have any semantics except at the assembly layer. So this is a binary. It's also, well, it's specifically a 15-bit positive number here. Right, So maybe we have an unsigned 15 type for that. Yeah. And how we define those types will, I suppose, depend on how we are using it within the state machine. And in the C instruction itself, let me pull this up here. So the C instruction kind of looks like this over here. This first bit is telling us whether um, we're interpreting A as like a memory location or as a constant value in itself, right? So A, just whatever the value is in the A register, or reach out to the memory in that address, dereferencing A, right? And the next 6 bits are what would go to the ALU. They're the opcode. And yeah, this is basically like negate. It's down here in this bottom corner. So like we have an X and Y argument to the ALU, right? So we're either zeroing out one of them or negating one of them, possibly. We're choosing between plus or bitwise and then we might negate the output. And that combination of little flags allows us to do a pretty wide variety of operations. It fits all of these. So that is what's being represented here by this comp class. This is the computation. I'd had here just the 6 bits. Probably we want the 7 bits. And at a higher level at the assembly, this will be a lot more semantic. It might be like add, add x plus y or something like that. And we'll have a way to translate that down into these computations. And it's probably like the first real real thing we'll implement. Besides, like actual implementation, not just modeling here. Um, okay. Destination. Which of these are we saving to? So that's those 3 bits. That's pretty straightforward. These 3 bits up here in the top right. Um. Oh, okay. I have a little compilation issue here. So when we're parsing this from binary, we are taking these 3 bits. Oh, I'm not sure this looks exactly right. Yeah, this isn't exactly right. So I could do it this way. I could bit shift it. What I think I'll do. So for each of these, I'm gonna check if after we mask it, we get that same binary, right? Those 3 bits mask, and it's that. Oh, except. No, no, no. All we care is that if A is set, it just means that that one. I guess yeah, that would be it if we mask it for that first bit there. Which let me double check the order. In the top right, this is actually M, D, and A. So we are backwards. Great. We'll just call this M. We'll call this A. I'm gonna switch those around. You know what? Actually, we're not gonna switch that around. We're gonna match the manual here. Okay. So if we mask that, then it should just match with that bit. And if it's equal, then that boolean tells us to use that. Okay. And then when we're parsing the whole C instruction, we're gonna have this flag here, which I might just put into the comp. And then we just recursively parse the destination and the jump. Yeah, I will include A as part of the comp. I think it kind of makes sense to do that. So let's add a new field here. So from mem is going to be a boolean. And when we're parsing this, we have from mem equals, I don't know yet. It's going to be whatever this is after we properly make that compile. I think we're just missing parens here. Okay, so we shifted so and so many bits. Yeah, I don't think we really need to do it that way. I'm just going to delete that line altogether. I'm not going to have this from mem in the C instruction. And then here we're going to define from mem by doing something similar to other lines. We shift this one the most, so it's going to be shifted over 6. Okay. And we're doing equals 1. I think it suffices. If we're masking against 1, it suffices actually just be like not equal to 0. So let's just do this little micro optimization. A viewer had commented that last time. All right, and what's going on here? We found a comp and we required a C instruction. Oh, right, C inst right here. Constructing that. Okay. Here we're shifting over. I think I want to call this opcode comp actually, because that's what this whole thing, these 7 bits are called comp. So we'll call it what's called in the manual. Or, we could call it the comp bits if we want to be like accurate. Okay. And then, right, this is going to be, I guess, an int. What's going on here? Literal constant type. I guess we can do that. You know what? We can let the compiler optimize this. I think I just commented that, like, this thing kind of thing can be optimized if we really cared. Okay. Or like, it would be inlined into here. And I think the compiler can actually figure out how to do it that way on its own. Or not, or not. I'm not actually sure because this n might not be knowable enough. Okay, so let's revisit. Let's revisit the ASM package. All right, this is where I got the most hand wavy. It was near the end of the stream. So let's try to make proper sense of this. So we have an assembly instruction, and they look like, let me pull this over. This is what the assembly text looks like. And there's two stages when translating assembly. So first, like we have to remove all of the variables, basically by like getting well, we construct a symbol table, and that allows us to remove all the variables, and then from there we can just translate it sort of line by line. Um, yeah, I think I might model that. Let's see. I might want to save this as a different file. But basically, we're going to have a method like this. So assemble, and there's going to be an assembly program. What's an assembly program? It's going to be just a list of assembly instructions. And to do that, there's two phases. Well, let's see, what's going to be like the end type? The end type is going to be, I suppose we do like a list of, we get a nested packages like this so we can reference ML. So ML dot instruction. Yeah, a list of binary code. And that will have two phases. Basically, we get a symbol table. Um, yeah, so we're gonna get some sort of symbol table from this symbol instruction. Oh yeah, there we go. So let's just say this program. So an assembly program is for now a list of assembly instructions. We might type that more later. And we want a method like symbol table. Yeah, symbol table out of a program by kind of rolling through it. So from a program, and actually we kind of get. I'm gonna do basically two methods here, two helper methods for this assemble. So we're gonna get the symbol table, and it's gonna be a map from a symbol, I suppose, to a value. I guess it's gonna be a binary value. It's gonna be one that's representing an address, though. Um, yeah, I'll just note that. So, so binary represents an address. Maybe not all the time, but I think it should. It probably does. Um, if we figure out what it does, then we can encode that. And then we're going to have some sort of method like translate. So then we need like a program and a symbol table. So, just like up here basically. Let's just inline it all for now. So symbol table is going to be map from symbol to binary. And then okay, so yeah, we get the symbol table and we result say that we put this in the program. I'm just gonna save the intro over and over again. Sorry about that. Let me get this list of ML instructions. Yeah, we do everything that symbol. We're gonna translate that thing to the symbol table. I don't know if I like to use signatures, but that's communicating the rough idea of what I'm probably gonna do. Uh, Declaration is not allowed in here. It should be in Scala 3. Really? Top level of a package. Um, maybe something like that. Okay. And these here are like forward references. Oh, yeah, binary is not really defined here. All right, let's leave this commented for now. Figure out what we're doing there. Once we should figure out the rest of the model. Um. Anyway, back to looking at assembly. So we have an assembly instruction. There are all these symbols. There are three types of symbols. I think I want to open up the book here. Yeah, so there are predefined symbols, label symbols, and variable symbols. So the predefined ones are just ones that get translated basically directly into um, 0. So like, we have the virtual register, so R0 becomes 0. Stack pointer SP, local that becomes 0, 1, 2, 3, 4. These are like hard-coded values. And I have half a thought that we have this program, but we also have like a dereference program where we don't use any symbols at all. Right? There are a lot of these things that work with either a constant or a symbol. And once like you dereference that symbol, it becomes essentially a constant of some sort, right? I think all the symbols eventually just do get replaced by constants. So maybe we have a type parameter on the assembly instruction itself. Like, is it dereferenced or not? Or like a different type hierarchy. If we're like saving two different representations, which I'm not sure if we want to do that yet. So we have this, yeah, these predefined symbols. Virtual register would be one of them. So extend virtual, virtual register would extend our predef symbol. As with all of these. Now these all have a value. All the predef symbols. So let's do. Actually, before we do that, I just want to see that are we in a compiling state? Yeah, we are in a compiling state. So we can refine things further. Okay. So any predef symbol then, which like these I might move into their own file. But we'll see. There's going to be a value, which I suppose is going to be a constant. A constant is just an int. So whatever we were saying binary up here, we probably mean constant. Constant is like just an int for now, but might mean something else eventually. So def value constant. Yeah, that can remain abstract. So for a virtual register, def value equals this match. Actually, we're not going to do a match. We can just do like this dot ordinal, right? R00. Actually, I'm gonna strip the leading zeros there, but this should just be 0, right? So forth, as long as those are defined in order. Let me just remove R0, replace with R 6, 7, 8, 9, 10. Okay, those are the register names. Okay, and now each of these case objects does have to define their value because they are also predef symbols. So let's do it this way. Or you know what? I was thinking I could match. And if it's a virtual register, I do ordinal. And then if it's one of these, I do predef symbol. And screen and KBD are also going to be values here. I might give this a parameter. Yeah, if we did that. And then if these extend, well, actually this here gets hard to define. Let's not do that. Because I kind of just wanted to like do this, put the number in there. We could give it a new name like hard-coded symbol. Or we can just match this way. So we'll define a log up here at this level. So this match and case should be an autofill here. That just makes that complete. Well, you can do it manually. Um, would kind of be nice to just make these an enum to, but we'll make it explicit here. So case each of these. Then we have 0, 1, 2, 3, 4, and screen and keyboard. And then like we have a match case for this virtual register. In which case we just do like r dot ordinal. I think I just want to do this as an enum. Yeah, I think that's actually what I want to do. So we're going to do an enum. um, so this extends predef simple. And we have case sp local arg this that screen and kbd and that value. So we're going to match on this. I should just have an autocomplete for the whole match coming from the editor here. Okay, yeah, so we'll define the values in here. This should be the main abstract. All right, I'll check out recurrent compiling. Okay, so this match so for each of these, we'll have a case. Um, okay, stack pointer 0, local 1, and so forth. Except that screen is 0x 4000, keyboard is 0x 6000. Yeah. Yeah, I think so. All right. So symbols transform into constants. The predefined symbols have their values already defined. And the other two types of symbols, we have labels and variables. Okay, so the label symbol defines a symbol XXX to refer to a location in the hack ROM holding the next instruction in the program. So that gets turned into an address. Well, a constant representing an address. I wonder if you want to keep that. I think it'd be nice to keep that information. But for now, we won't overly refine that yet. You want to get, we kind of want it to get sort of working, and then we can refine it. and see if we can understand more as we continue to refine it. So there's a label, and there's a variable. So an A instruction represents it can use a constant or a symbol. And when it's using a symbol, is it usually a variable or could it be multiple things? Let's see. So an A instruction, we have these, yeah, they're the ones that start with the at here. Yeah, you can use that with any symbol. Right. And basically the first pass allows us to turn that into just straight up constants. Um, okay, so there's this stuff which is all in service of a computation, a C instruction, which has a destination, which can be a set of A, D, or M, a computation, and a jump. And I think we probably hand waved this comp a little bit, so we'll look into that more in depth. But this dest, that feels good enough. There are three possible destinations, and we're like doing any set of three of those. And these are the 8 jump possibilities. Um, left side is 0 or D, right side is 0 or I guess of a computation. Um, right. To do A plus M, etc., is not possible. To do like right, so like we possibly want to add a constraint. Okay, when we're doing a computation, there's always gonna be a left hand side and a right hand side. The left might resolve to 0. Like this is part of like a binary operation. A comp actually should include a destination. Well, a C instruction has a destination. So the left-hand side of a C instruction is the destination. Um, and that is actually optional. We're representing as a set of destinations. So an empty set represents no destination. What we just encode that? Let's just say object dest. Let's say no dest is going to be set.empty. Um, okay, nice to have that. Something that's technically legal. I don't think there's ever a reason to do that, though. Or, ever like a good reason. Stress test. Okay, something about this add left and right. So the right side is either a register or a constant. And when we say register here, I think we mean wait, what's arg? We're not actually using this arg here. Register is a reference to either AD or M, like a virtual register. I guess that's what we meant by our argument. Okay, so we have something like D equals D plus A, or we have here's our list of computations. I think I do want to have an assembly parser, and I'll parse that into here. As opposed to a DSL, I played with the idea of having an assembly DSL that would look something like this here, or maybe something nicer than that. That's something I want to give a little bit more thought to, maybe. But handy when we're writing a bunch of tests or generating a bunch of code. It's probably how you might want to do it eventually. So when you have something like D plus A, left side is either 0 or D. So this should just be register here. Right, something like negative D is basically going to be, so this was actually, D always on the left side. So this is like D on the left negated plus 0. Oh, but we're not going to represent it that way. We're just going to have an explicit negate here. Okay, so this register then, that's what that means by this can be AD or M. Um, or const, right? And with a not, we can do that to AD or M. So registers AD or M in this case. And here the left side is, I think I'm content with making the left side be just register because we don't ever do like 1 plus M, right? We always represent it as M plus 1. So that means the left side here can be any register. The left side of add, so that can be AD or M. Yeah. Now something like M plus M, you couldn't actually write that, could you? Yeah, like you can never really add something to itself. That might be enough of a constraint once we're adding this constraint. So we'll add a note. Note, never add a reg to itself. Okay. And this register is actually just AD or M. I could use the same thing as using in dest. Like dest can be a register, like a set of registers. So I might rename that. Yeah. Mhm. Yeah, we'll do that. And then we use registers in both those locations. So register and as like an argument sometimes. We're not using this arg here. So I'm going to delete that. I'm going to delete this. I'll leave these notes here just for myself as I'm wanting to add constraints later. And we can do object bridge test. It's just going to be a set of an empty set of registers. Okay, like this is good enough that I can actually write a little compiler. So perhaps like that's our next step. Not a compiler, like a parser. And I could use this here as an example program. Um, labels and variables. A label has a name, a variable. Let's take a look at labels and variables again. So this is going to be like this is the parens. That's this here. These are labels. That's going to be like a ROM address um, of this instruction. So as we are parsing, you'll want to keep track of that. So actually, interestingly, like a program isn't just a list of those. It could be a label, like maybe an instruction. One of the types of instructions is a label. I mean, it's not really an instruction, but anyway, a line. So a line can be an assembly instruction or a label. Let me just write that down. So like assembly program can have well has lines, lines comments. Um, should check if empty. And what else? Um, lines can be labels. Any line that is not an instruction does progress address. Okay. So I guess each line, we could say a line has an optional comment, an optional assembly instruction, and an optional label. All right. I think that's a fair way to do it. Let's let's write that down. So case class line, and the program is going to be a list of lines then. So there, the first thing is going to be a label. Um, and that's optional. So an option of label. And of course, this is us kind of, well, there can be multiple comments. Um, well, I mean, no, those still are like separate lines. So there's an optional label, there's an optional instruction. And I'm going to just rename assembly instruction because it's already kind of prefaced by assembly package. And it optionally has a comment. And that's all we really care about when we're parsing lines. Okay. Yeah, I think when that is our next step, we have a good enough model here to represent something like this. And we can test parsing that. And I think for a test, I just want to do that in a worksheet. So let's make a new file. We'll call it test.worksheet.sc. And we'll just import everything from Nand2Tetris. So we'll get there eventually, but we will want to translate this sample program and see if we can construct the same symbol table. What our assembly package. Okay. And these symbols can appear. Oh. So when you have an A instruction, it can be a label. It can be a label, right? So here's an example of I is a variable. Loop here is a label. And R0 here is a predefined symbol. I'm still not sure that I like having the distinction of hard-coded symbol as a type of predef symbol. I'm really only doing that for the convenience of this. Like I could have written this like so. Say this object SB extends predef symbol def value 0, right? I think I prefer that to all of this, but that might be annoying once I start giving predef symbol other capabilities. So I won't refactor that now until we know for sure. Okay, I'm gonna leave this on screen for a sec. I'm gonna take a little bio break. And when we come back, we're going to work on the parser. All right, we're back. So we're gonna work on the parser here. I'm gonna start separating this into smaller files at some point. Um, let's see. I'm thinking about how I want to model like the assembler itself. If I make a class here, I really just want to have um, a small collection of methods. Let's mess around with this in a worksheet, and then we can put in the file as we see fit. So let's go to our little test worksheet. Yeah, and let's do a parser. So this is going to be a list of lines from a string, I suppose. Um, so I'm just going to translate this test program. I'll do that by hand. And I suppose I just have to write that out by hand, don't I? All right. So we can comment on it as I'm writing this out. So this is a program that computes R1 equals 1 plus whatever all the way up to R0. So R1 and R0 then are our arguments. Everything from, yeah, it stores into R1 the value of 1 through R0. R0 being like our only argument. Great. So there's this comment, I equals 1. It's explaining what we're about to do here, which is going to be at I, so set the A register to, I guess, the value of I, which doesn't have a value yet, but it's going to be, so I is going to be some memory address, right? And it'll be initialized to 16. WFM Macaw, hey, good evening. It's been a while. How have you been? Um, yeah, just getting into the parsing stage here of assembly into kind of my model of an assembly program for the hack architecture. Okay, so this means we're going to say the value of I, which I is going to be assigned 16 because it's the first unreserved memory location. So R0 through R15 are all reserved, right? And it's interesting. So like loop here, loop can be 4 because that is a ROM location, not a RAM location. So we have two types of constants here, and it is either ROM or RAM. Let me make a note about that because I would love to be able to distinguish that. Oh, why is it emoji? So, constant could refer to ROM or RAM. Do we always know which? Because like the dereferenced version of this program, I might have two models, one for like the raw assembly and another for like the reference version. And in the reference version, we might want to know, it might be helpful to know that a constant is referring to ROM or RAM, or actually just to, it could also just be data. ROM, RAM, actual data. In this particular program, I don't think we're ever using it as actual just data. Those are all memory locations. But like in theory, you could write a program where you just said like at 500 and then did something with that. And that's how you'd like plug in a constant if your program had constants in it, which this one doesn't really, because all it does is increment by one at most. Um, Let me just look through the book. There might be better examples for us to use in our translation. I'm gonna flip through. I'm gonna start flipping through a bit of the book off screen. I think if I want this to be fair use, I should only be showing the parts that I'm using of the book. But if I like flip through the whole book, then I'm kind of like just sharing the whole book, right? Um, I think this part is worth reading to the stream here. Oh, you saw my VODs. Yeah, thank you. I'm excited for it too. I'm especially excited because it's so open-ended and it can go in any direction. And this one, much like the Cinecore project, it's not on a timer like Decode is, so I can kind of take my time and distill things. And that's nice to, like fully understand something and then get to play with it a little bit. And I think this time I will want to make um, summary videos because it's gonna be like a much bigger project, and I want to like summarize like, hey, this is the final architecture, what it ended up looking at the end. Because I think, well, my goal is to have like a final architecture I'm a little proud of. So the hack machine language specification, I'm reading here from the book. Um, the assembly language and its equivalent binary representation were described in chapter 4, and we're repeating it here for ease of reference. Oh, okay. It's the contract that hack assemblers must implement one way or another. Right. Yeah. We should read through this a little bit. So there's a binary hack program. Um, zero, right? Yeah, 16 bits. Each text line is that. If it starts with a 0, it's an A instruction, address slash constant. Otherwise, it's a C instruction, some opcode, some computation, address and computation instructions. Uh, and an assembly hack program, each being an assembly instruction, a label declaration, or a comment. Oh, yeah, I guess it's an or, isn't it? So the way I'd modeled it here, I'd I'd modeled my lines as being optional label, instruction, or comment. Like in theory, like I was thinking it'd be nice to be able to put the label on the same line as the thing itself. But that does make parsing it more complicated. So maybe I'll add that later. Um, yeah, so align then. Let's write this differently. So type line is going to be label or instruction or string. String being comment. We can say that. Let's use aliases. Okay. Yeah, I can conceive of how like you could do that, like add comments after that line, etc. This does simplify things a little, I think. And we don't have to validate weird cases where like there's neither of those three. Where, like we have a blank line or something like that. But we'll leave this as a to do extend spec to allow label its comment on the same line. Okay, back to the spec. And that makes it super easy to parse because the label will always start with a paren. It looks like the instruction will always start with an indent. Okay, we've gone over symbols. Syntax conventions. Here, this is what we need to do for parsing. A symbol can be any sequence of letters, digits, underscore. Okay, great. So it's not just a string. So we'll need like a validator for parsing that. Um, any sequence of letters, digits, yada, 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 that does not begin and oh, that does not begin with a digit. So we can use a regular expression there. Um, Constants may appear only in A instructions. Yeah, this program here doesn't use constants. If I go back to the spec real quick, I think I had a question. Um, because when we're interpreting these A instructions, it is a constant or a symbol. We use constant elsewhere too, though. Oh, okay, we have two different kinds of constants, I suppose. So there's a constant that we're adding in. This const here is actually just like 1 or 0, right? In the computation, the the constants that we use there are just like 1 or 0 because that's what we can kind of fake by giving the ALU certain like opcodes. Um, right, and after a pass to create the symbol table, basically every symbol then gets mapped to a constant itself. Um, but not just mapped to a constant. So when the symbol table gets mapped, everything it gets mapped to represents either a RAM address or a ROM address, right? Like loop here references an instruction address for I represents like a RAM address. And the other constants that are remaining were things that had been specifically a constant. So there are, once we do the parsing, then there are three types of constants. So if we end up having like two versions of an assembly program, one that's dereferenced, um, what was that question? Or RAM, ROM, or data? Yeah, so this is lying a little bit. I think I want to continue calling those constants. Um, well, I guess RAM or symbols can refer to ROM or RAM. And deref to constant. Hard-coded constants stay unchanged. And should probably never reference memory. I mean, as a programmer, you're probably free to do that, maybe. Can we tag those values? This is not anything I'm going to do now. I just like having these notes because maybe at some point, if we're doing like some transformation in the program, that will be interesting to play with. But chances are I'm just going to represent this as an int for now. Okay, so we need a parser for the symbols. Constants may only appear in A instructions. A instructions can also have a symbol. Okay, there's leading white space that we're going to ignore. Case conventions. I think I'll enforce the convention. All assembly mnemonics must be written in uppercase. Oh, it does say must, so I will enforce that. The remaining symbols, labels, and variable names are case sensitive. The recommended convention is to use uppercase for labels and lowercase for variables. I think I will enforce that. Oh, and that is a full specification. Okay, so this bit, I can't copy paste, can I? Let's at least add that parsing for a symbol. So I'm going to do that here in the lower bit. Um, so I guess variable and label. These both need parse methods. Maybe I will do a symbol that parse method. Let's put that all on screen. So object symbol def parse. So there's going to be a name. Okay, and in the case that it's one of the hard-coded ones, let's do this name match. Let's start with these up here. And we can hard code it this way, right? Just strings with the or between them. All right, just gonna do a little bit of boilerplate work. So I can just multi-line this. I should just get Copilot back so I can have Copilot do this kind of. I'll make a note to myself to do that for the next stream. Because I want this to be all like human generated slop, but it's nice to have AI handle some of the boilerplate for the sake of time. Yeah, I did that. I didn't need to do it that way. I can also, if it starts with an R, let's parse it properly this way. So case, so we have a string R, and then we have index. If index dot to int option is what? It's going to be like 0 through 15. Um, actually, I don't want to allow parsing something like 0, 0, 1. All right, if you pull up a REPL, right now parse is 1, so I don't want to parse it that way. So instead, I can do 0 to 215 and just map that to string. And we can call that our indices. So our reg indices is just going to be that value, all those strings. And probably we can, this is something where we could probably like inline that hard code it too. We could just take that. Okay. So once we have that register name, then I suppose, well, we can take the ordinal. We can take the index and map that to an ordinal. That's a way of parsing that. Or can we parse it from a name? Yeah, we're gonna take the ordinal, so we're gonna do index dot to int. And do like virtual register that from ordinal. Okay, and this gives us a symbol. So that handles one case. And I suppose I could give this its own parse method. Raj Codes, thank you for the follow. Wait, why isn't this auto denting? Okay, so case, let's say we have SP. Actually, I want to defer this to, I might want to defer to this, like parse that recursively. But for now, we'll do Actually, I'm not sure how I want to parse that. The whole point of coming here in the first place was that we wanted to parse strings into, yeah, we wanted to parse strings into symbols. So this is going to be just SB, right? Um, and then etc. And here's the code I'm actually writing. It's a label or a variable. So if it's a label, it's going to have the parens. Are we going to pass along the parens? I'm not sure what we're going to pass to this parsing here. I don't think we should parse all symbols together, actually. I'm going to return to the broader parsing method real quick. Um, and see how we want to structure this. So program is going to be string, and we want the lines from that. So val raw lines equals program dot. Don't we have like a get lines iterator? I forget what it's called. What did I do in the code? Yeah, just lines. Lines iterator is what we want. And I think we want a method that does just one line at a time. We'll just map over this. Raw lines dot map. And then we're going to do like a line match. So we have I suppose first we want to trim the line. So line not strip. Line dot strip. Is that to both deleting end to end? Let's just look at the documentation real quick. All leading and trailing removed. Okay. Yeah, I'm cool with that. Great. So if it starts with a comment, and then we can just pass that comment back directly. Let me change the music real quick. All right. And at the end of all of this, we're going to do like a to list or something on that iterator. So we strip. There's a comment case. If there is parens, and it's going to be a label. We'll want to assert that that label is uppercase. Label is up. Is there like an is upper? No, I think for all characters we want is upper. Okay. Uppercase labels by convention. And we do a label with that name. Cool. And if we have an at, and this is an A instruction, what's going on here? Out than expected, but I'm not seeing a syntax error here. I guess we could do that. Sure. Okay, so this is going to be an A instruction. So this is a constant or symbol. We'll parse those two in separate cases. So here, let's say there's an at and then constant. And that's a constant if constant is a string or to int. I'm not getting my autocomplete, which tells me there's like an issue here with the parsing. No, it seems happy enough. Case found up to expected. Did we miss like a no, my syntax error here is okay. Well, we're interpreting this as a constant. I know there's like a method for this somewhere, like here. 3234 dot is or like all digits. I guess two options the way to do it. So val, we'll just say n. So n equals constant dot int. And let's do a little assertion here. So assert, because constant has certain values, 0 to 32767. And that is just 8, I don't know, 7 FFF. FFFF. Not that many. But this is just 16 bits. 32767. Okay. And this assertion I should probably move into, I don't know, a constructor for constants. Yeah, an instructor that kind of like type tags it. Um, so constant around like constant dot to int, right? And if you go to constant, oh, right now constant is just a type alias, but we can at least add this method. So object constant def apply. So it's some int, and we're gonna get the constant out of it. Um, and we're just gonna give n, but first we're gonna add a requirement here that 0 to 0xf, wait, 7ff of this range contains Rn. R unsigned 15-bit. Okay. I don't know what we don't like about this here. Oh, I see. The indent was wrong. One sec. Required yeah, a list of lines. So we're getting string or label or int. That label should actually be parsed as like a symbol. So a label is a symbol, right? Um, it's not liking this because string or label int. I guess we could cast this up to a symbol for now. There's gotta be a better way to do that. Where's this file? Let's put a type in here. So we're gonna map this to a line. Found a symbol, required line. And what's the definition of line? Line is a label or instruction or comment. Oh, that's not quite right, is it? No, no, no. It shouldn't be symbol. Yeah. It should specifically be label. This label is technically a symbol, but it's kind of treated like it's treated differently from other symbols, and I'd like to make that distinction at some point. Okay, and this constant expected align required constant or found constant. So our line is label instruction or comment. Oh, this is actually an A instruction. So this is an A instruction. A inst. There we go. All right, and if it's not parsable as an int, then we assume that it is a label. Well, not a label, but like a variable. Or a symbol, generally a symbol. And that could be any kind of symbol. So we have at symbol against yeah, and then we parse that symbol. Okay. So I'm liking then our earlier like parse method. So we had a def parse symbol.parse. I suppose we could call this like constant.parse too, because it can like fail. We're not just like constructing it. So this apply, I'm going to rename that to parse. And if you go back to symbol.parse here, okay, so I don't think we have to worry about then like the parens. The thing is, we won't know. We don't necessarily know if it's a label or a variable, do we? Yeah, it is really just a symbol. Uh, right, because if we look at this, here like we have an at I, at some. We only know that those are variables because they're lowercase. Hmm. I think I will parse it that way. I think we'll make that a rule here in our assembler. Lowercase must mean a variable. Yeah, our variables must be lowercase and labels must be uppercase. Because it's a good convention, and I don't want to run into like any hairiness that comes from. Although, I suppose those variable names could totally come from like a program that's being compiled. We'd have to make sure that our compiler and upper level adheres to that, right? And we might not want to for like good reasons. Hmm. Yeah, it's just that, just a symbol. So we can't distinguish between a label and a variable. Let's see if we regret this later. I'm I'm going to make a rule here. Now, uppercase is a label. Name if name dot for all is upper. There's no is upper. Name's a string, right? Is upper. There we go. So in this case, we will just mark that as a label. And then we'll do a lowercase version of that. So if it's lower, then we're going to parse that as a variable, var name. And then we'll have a fall through case. And we'll just throw an error. Symbol isn't label or flower, and we'll just show that symbol. Okay, that will do us for now. But then that allows symbol.parse to parse any of these hard-coded symbols, any of the virtual registers. Yeah. Just gonna copy paste these. Hard-coded symbol dot paste. Okay, this parses all the possible symbols, I think. Yeah. Let me go back to our main parse here. So we can parse an A instruction that does a constant or an A instruction that does a symbol. Good. Now, otherwise, what's going on here? Is it happy? Cool. Otherwise, we might have something with an equal sign. So there's going to be a dest equals comp, and then there's a semicolon, and then jump. So there are a few shapes it can take because dest is optional and jump is optional, right? Yeah. But let's parse this big version first. So destination can be multiple. Yeah, we'll write a recursive parser for each of those. Let's see, do we already have one for? All right. Let's go into definitions for each of those. Dest. Oh, register. So dest is a register. Register dot parse. So I guess we parse multiple registers. And we have a few constraints. Yeah, we're doing like a completely hand-rolled parser here. Like this is a case where like, I don't know, making it, using a parser combinator would make this more clear. That like say the dest is only AD or M. Instead, we can just do that as an assertion now. So require s dot size equals. I suppose we could have a dest dot parse, like register dot parse destinations. Yeah, Scala has value types. Also, welcome. Thanks for popping by. Okay, so I gotta go to the bathroom real quick, so I'm gonna write down what I'm about to do. So dest is either AD or M, some subset. Comp, what's it gonna look like? Is gonna be well, this stuff here. Um, thing is, I want to. Oh, right. This is something I'm not going to be able to. I think I just want to translate that directly. It would be easier to translate that directly into machine code, wouldn't it? Okay, I've written myself into a corner where I still do want to have like a representation of the assembly. So we'll just have like a little bit of a pain parsing this into this assembly model, parsing like the string version of it into it. Because I don't want to go from like string to bits. I want to have like an actual model in our space. Um, and then the jump. Used to be pretty big on combinators as well, but lately you fully embraced the tokenizers and personalizing approach. Yeah, that's fair. I mean, like this is designed to be like very easy to parse, like no backtracking or whatever. So like recursive descent just works fine. Yeah, Scala has a pretty robust type system. Okay, I'm gonna leave this up on screen so anyone who's showing up new can work out what's about to happen. And I gotta use the bathroom real quick. True facts. All right, be right back. Oh, hey. Thank you for catching that. I always appreciate it. One of these days, I'm going to make it automatic so I see that I'm muted. Um, yeah, so I'm just parsing the individual characters. And then we'll throw in some constraints here, like, I don't know, at most length 3, assert raw dot length is less than or equal to 3. And it should also be non-empty, right? Otherwise, we shouldn't even be in this parsing code. So raw dot set. Um, right now. It's not. I don't know why it's not like this text here. We have 3 cases. And like ideally, nothing should be repeated. So if there's anything else, oh, whoops. So if it's anything other than AD or M, that's like an error. We're fine. Make our error types whatever later. I'm just gonna do like underscore unmatch here. And then we're getting that into that. Oh, we also want to check that there are no duplicate, I suppose. So you want to check that. I know. We'll do an assertion here. Regis dot size was Regis dot modest. Make sure there are duplicates. Or Regis dot what's the message for calling for like deduping it? Man, it's been a minute for me, hasn't it? Whatever. I'll comment that for now. Regis dot I'll make up a method name now. Okay, so we have a way to parse registers. Types of string and character. So these are actual characters, not strings. Okay, so we can parse a destination. So reg dot parse dest there, and it's going to go into a C instruction. C instruction, and here's the dest, and then we have a comp. It's going to be a little bit more of a pain to parse, and then we have a jump. So let's go parse the jump first. There's a jump here somewhere. Okay, so the jump is just going to be one of these. It's just going to straight up be one of these values. Yeah, it's just going to straight up be one of those instructions. I feel like an enum should give us a way to parse by name. default node library. Let's see. Object jump. So let's define a parse method here. Def parse from a string. And it's going to be some jump instruction. And jump dot from value of the name string. Right. Yeah, that's it. Okay, jump dot value of raw. Cool. And null should never actually be passed in there. So let's just add that as a requirement. Require raw is not equal to null. And if it's anything else, it will just fail here. And we can add like better error handling later. But for now, we just want to get it working. So jump is going to be a jump parse that jump. And what's going on here? It doesn't like, we need a line. Right, a line is either label instruction or comment, and a cinst should be an instruction. Cinst. Yeah, it doesn't extend. Here we go. Extends instruction. Okay, and then we'll make a parser for the instruction. I could be parsing these separately, so I could parse a destination if it exists by just parsing the first bit here. And we get an optional dest. But I think the point is like once we get here, we've parsed out comments and labels and A instructions, then it must be a C instruction of some sort. Because otherwise we're handling alternative cases and just rewriting a bunch of similar code, right? So like comp jump or just a comp or no destination. We'll try it this way for now and see what that looks like. Otherwise, like we might push this parsing down into cinst and just parse like the front bit first, an optional dest. And equal should not be valid. You know what? Actually, I think I do want to do it that way. So let's look at C instruction. Add a parse here. Object C inst def parse raw string some sort. We're gonna get a C instruction. Okay, so there's gonna be a dest, and we're gonna check if the instruction has an equal sign. We can parse destination if it has an equal sign, like an optional def parse dest, and then return the remainder of the string, and then pass that on to be parsed. So it's gonna be like a string and a set of registers. Okay, so here, if raw contains an equal sign, then we do what we were doing a second ago. Do this reg.parse test. Reg.parse test. And it's gonna be raw dot. I suppose we take everything until the equal sign. So let's do val test and remainder. Because all that split at. The index of our raw string, or of our equal sign. The index of yeah. So we parse that dest. And then we also pass along the remainder. I'm gonna drop one, drop the equal sign. Otherwise, we're gonna do reg.no_dest. It would look something like that. I think for clarity, I might actually just rather have the very verbose version. Declaration of a parse method is not allowed here. Oh, that's interesting. I don't believe that. Oh, right. There's an arrow here. Um, there's a reg.no dest. Yeah. Oh, right. We also have to have the remainder. So in this case, the remainder is just the raw string itself. Okay, we'll keep doing that. Let's do method signatures for the rest. So def parse comp. So here we take string. So this is going to be a comp and the remaining Is comp also, wait, comp is mandatory. Right, the comp could be like 0 or something. Yeah, if we're just going to do like a jump. That's why we have something like this 0:jump, just a non-operation. Um, I think we can parse comp last. Let's parse an optional dest or jump. Parse jump. So from a raw string. So this is also going to do like a tuple. It's going to return a tuple of a jump and the remaining string. It's still unparsed. So if raw contains the semicolon, then we do some actual parsing where you can do the same kind of thing. Raw.split at. So we have like the remainder first, and then we have the jump at the end. Raw.split at the semicolon, or the index of semicolon. And then jump.parse at jump. And we also return just the remainder. It's jump, you have to drop one. Dot drop one. Yeah. I think I will want to rewrite this, but it works. So otherwise, there's just no jump. Otherwise, it's going to be jump dot null. And the remainder string is just going to be the whole raw thing. Okay, do that chaining. I think I have a nice way to syntax this together. So we're going to parse dest out of the raw. And where's our like pipe? Yeah. So from here we have a dest and a remainder. So we're going to parse jump out of that remainder. And from here we have a jump and remainder. And then we're going to parse comp, where we're going to do a comp dot parse that remainder. And construct the whole cinst. So cinst dest equals dest. God, what was this parse thing here? And cool. Could not infer the type parameter. Well, parse jump does give you. You shouldn't need that type parameter. Like it knows this is a set and a register, and that this remainder is a string. We're passing in that string. Oh wait, missed a dot pipe here. There we go. Okay, and this method does not exist yet. So let's go to comp. Um, and add a parser. Okay. Yeah, this is all information we need, isn't it? So we could look for an operation. Um, hmm, and then I suppose so we could look for something like plus. Plus is always a binary operation. Um, we'll need to disambiguate between sub and negate. Oh. Um, yeah, we'll need to disambiguate between sub and negate. Otherwise, we can just look for the binary operation and individually parse left and right. So when we're parsing the left and the right thing, it can be any of ADM, a register of some sort, or the constants 1 or 0. Oh, const. You know what? 0 is never really used as a constant in a binary operation. So there is just 0 here, like as a top level. Hmm. Okay, worth noting. I'll just note that for now. Const is never 0. And that's the same like up here. So an const on the right hand side is never 0. Okay, so we'll note that. What's our plan here? Look for item gates of neg, big weight, big weight. Parse for reg or see LHS and RHS are different. So parse left and right hand side differently. Um, otherwise, parse memory off, which is just gates or a not, or just straight up a register. I could do like I could remove const from the top level and just make that a no-op because a no-op could be a register, right? So we could have something like case class no-op, and it's just a register, kind of like maybe mount, or like kind of just which means that yeah, const itself no longer has to extend. comp. Okay, that kind of works. I'm not in love with it. So that's probably something that after I sleep on it, I'll want to change. But it does work. Multi-parse otherwise. All right, I think that is fair. So we want like a helper method to parse by and up. And that'll be an option, like an option of option comp. Okay, so we're gonna do option dot when raw dot contains plus or and. I guess we're assuming this is well formed. I don't think we'll do raw dot contains. We'll look at the second character. Mm, no, let's not do it that way at all, actually. Let's do raw match. Okay, so we have left-hand side, and then let's do like plus right-hand side. Yeah, that's how we want to do it. So like in this case, we're gonna parse left-hand side and right-hand side differently. So left, can only ever be D. Well, I mean, left can be A. It's not actually. Yeah, so there's like an X and a Y, and the first op is always going to be like D or something, and the second op is going to be um, A or M or a constant, and whether it's A or an M depends on this A bit here. Right. So when I say left hand side, I mean left hand side here syntactically, even though the thing on the left side might this like this A plus one. A is actually technically the second operand because you would do that by zeroing out the first operand, which like the first operand is the one that can be D, the data register, and you would zero it out and negate it in order to turn it into a one. So this A plus one, technically that is the first operand there on the right. Um, anyway, so we could parse left hand side as A, D, or M. Right? It's always going to be a register. I don't think we have a register.parse, do we? Yeah, parse. Oh, it's essentially this. So I'm going to extract that into its own method. So parse raw string, and it's going to be a reg. And we'll do this. Or actually, we're just going to do value of. So value of the name. There we go. And then in this method here, we can actually just do reg.parse. Okay, I am happy enough with that, I suppose. Um, right. Parse works on the character. We want to turn that character into string. Sure. Not the kind of thing we're worried about optimizing now. What we want to optimize is the performance of the running machine, not necessarily like compilation speed of our assembler. Okay, so where are we going to use that? It's reg.parse c.toString. No, no, no. Here, so we're parsing the left-hand side as a register. And this is going to be in the context of an add. So left is going to be that. And right is going to be a register or a constant. So we want a separate step. Let's first attempt to parse it as a constant. So right is going to be a reg or constant. And we could do RHS match. And I'll probably extract this as its own helper method. There's not going to be a 0. I guess, oh, it's just going to be 1, isn't it? When we say reg or constant, that really means add or increment. Maybe I want to just model that as increment explicitly. Inc and dec. I think I want to do that actually. That way we're just parsing registers here. So +1 appears in its own kind of case that we match here. There. Yeah, I feel much better about that. So if we have like +1, so we have case class inc, and the arg is just some register. Yeah, case class dec arg is just register. Yeah, that feels much better. And we don't have to have this silliness. Your const right hand side is never 0, yada yada. Yeah, negating 0 isn't ever done. Yeah, I think we can, whatever's generating our assembly code, we can tell it not to do a -0. um, like technically, something you could write, but I don't want to have, there'll be a normalization step if that's the case. Right, that's the only thing that ever gets negated besides a register. Okay, which means one of our constants then has to be -1. If we're not putting it in here explicitly. And all of these right-hand sides are now just just registers. It does feel much cleaner. Okay, so left-hand side +1. This is going to parse as an ink. Reg parse left-hand side. I guess at that point it's not even the left-hand side. Yeah, I like not calling it left-hand side because it doesn't come off as like an op1. So parse arg, and that is that. So we have a -1. It's going to be a deck. Cool. And then this is just add. You don't have to worry about the weird right-hand side case. Reg.parse RHS. And in these cases, we'll add a to-do for assertion here, because left could always be D, right? That is always D, question mark. To-do always A or M. I'm liking that. It's feeling more and more constrained over time. Okay, let's do the other binops then. So case. I really should just defer to Copilot here. I'll have Copilot next stream for all this boilerplate. So we have sub, and I know. Let's do edge.parse, left-hand side. Oops. Side, edge.parse, right-hand side. And then we have or and. So we have, we'll do and first, and or. So this is and this is or. Okay, so that's all the binops. First register or 1. No op const. I guess at this point const can just be like high level again. Register or one of those 3 constants. All right. Actually, I think I want to handle like the negative case. We'll do not a negative. We'll want to parse this -1 earlier than everything else. Certainly before the negative. So I'll do this -1. I wonder if this could parse as an empty string here. So we actually probably want it above there too. All the negate stuff, I suppose, should be above the binary operation. Okay. So we have a 0, we have a 1, we have a -1. Okay, and then we have other cases of negating. And we have an arg. So it's going to be negate. And then we're going to parse that arg as a register. Reg.parse arg. Cool. And we'll also have a not arg, not reg.parse, that arg. Okay. Cool, cool, cool. This is feeling better. This is shaping up. That is all of our unary operations. That is all of our binary operations, including these pseudo-binary operations are just plus and minus one. We need just raw registers. So if there are no symbols at all, then we just parse it as a register, a no-op register. And I'm going to leave these to-do notes here. Because we might want to enforce that kind of thing. Right, and the final bit, case, I don't know, this is a register, reg.parse register, and we wrap that as a no-op. Cool. All right. And with that, I think we have a parser. I'm supposed to be logging off now. So this might be where I call it a night. And I might deny you all the moment of truth. Cliffhanger for next week. Yeah, let's go to this test worksheet. Comp, it's just gonna be comp.parse comp in that case. Or no, actually, we're just doing C instruction that parse that whole thing. C, let's name this dot parse raw. Okay. That does it. Yeah, so when we come back next time, we'll transcribe this. Actually, I might transcribe this off screen just to save you some like boilerplate. Or no, you know what? It's worth it to read through and think about what it does as I'm transcribing it. So I'll do that on screen. It looks good. Thank you. Um, I'm glad I'm making it look good for now. You can make Scala look pretty horrible. You can also make it look really nice, and it's not there yet. By the end, this will be super nice. There's all sorts of things I want to do, but we're not there yet. Yeah, no, thank you. Thank you for coming. Yeah, so next stream, we translate this. We run the assemblers that we're getting this into our model, and we're going to take that model. Maybe we'll have like some tests to make sure that's working, but then we're going to take that model and we're going to translate it to machine code directly to our machine code model. Which I think if we want to translate it to binary, we can translate it from the machine code to back and forth to binary. I'll do it in that direction. Um, and that should set us up for running like the state machine on the PC state itself and what each of those machine code instructions do. Quick question: is pattern semantics same as string formatting? It's similar. It's inspired by string formatting. Um, this was like an addition by Li Haoyi sometime, just like a nice convenience. So it's not like exactly semantically the same, but it looks pretty similar, right? Like a dollar sign is like the reverse. But pretty handy for parsing. It makes this look kind of pretty. Alrighty, let's find someone to raid, shall we? Um, Snow Cone. Oh my god, I haven't seen Snow Cone in ages. And she's doing leak code. We're gonna raid her. This is an easy decision. She has a very chill stream. It's fun to hang out there and chat. I remember reading a lot during Advent of Code. So it's been a hot minute. Alrighty. Thank you for stopping by. Thank you for pointing out whenever you noticed any little errors. And of course, feel free to ask if something's confusing. I want this to be like very simple to approach. That's why we're doing it long and slow. All right. Have a good night.